In our discussion of ordinary differential equations so far, we have addressed whether a differential equation has a solution, and if yes, whether the solution is actually unique. And in this video, we will discuss the stability theory of ordinary differential equations. So for comparison, when we discuss the theory of linear systems of equations, we are interested in questions like, is a system consistent? Does it have a solution? And if yes, is the solution unique? And then when we address the numerical analysis of linear systems of equations, then we also address the stability theory, such as if we have a linear system of equations, ax equal b, how does the solution x change if we shake the data a bit, if we change the right-hand side b a little bit, if we change the matrix a bit? That's typically not discussed in linear algebra classes because it is actually a question of analysis, but it is quite prominently addressed in the theory of, in the numerical analysis of algebra problems. We also address a similar question in our analysis of ordinary differential equations, namely, now that we understood a bit more about the existence of solutions and their uniqueness, we would like to know whether these solutions actually are stable under perturbations in the data of the problem. For example, if I've got an initial value problem that starts with a certain initial state and let it evolve, I would like to understand how does the system change if I shake the initial data a little bit. For example, if you've got an ordinary differential equation that describes a process in physics, then we would like to know whether small changes in the initial data have large effects on the evolution of the physical system in the long run. Understanding the effects of such perturbations is quite important in applications, and so we also address it in the numerical analysis of ordinary differential equations. Very concretely, we will have a look at the Cauchy problem again. So we have this ordinary differential equation, u prime of t is equal f of t u of t, with initial condition at time t naught. U of t naught is equal u naught. We have seen already quite a large number of problems that can be rewritten in terms of such a Cauchy problem, and the stability theory of ordinary differential equations addresses the following questions. For example, if I shake the initial data u naught a bit, how does this affect the evolution of the solution u over time? Or maybe I have a slight perturbation in my model in the function f. Maybe the function f contains a few terms that I don't know precisely. I know that, okay, these are some physical terms that are known with some measurement errors. So how do perturbations in the function f affect the evolution of the problem? What we're going to see is that the effect of these perturbations under some reasonable assumptions on the function f grows exponentially over time. One major motivation to address such stability questions is the fact that in many applications, we know the initial data and the function f only up to some measurement errors. For example, if we simulate some harmonic oscillator, typically we only know the initial data up to some measurement error, and maybe we know the material properties, for example, the frequency parameter, only up to some measurement error. And we would like to understand how large the effect of these measurement errors is in our understanding of the evolution of the problem. Let us first analyze the effect of perturbations in the initial data. And that can be summarized with the following theorem. Let us suppose we have got a function f, which depends on a time variable t and a state variable u. This function maps from the real numbers times r to the n into r to the n. So the first input component, the real number, is a time variable, and the second component in r to the n is a state variable. And for the theorem, we need a particular continuity condition on the function f. We need that f is a continuous function and that there exists a number L greater than 0 such that for all times t and all vectors u and v from r to the n, we have the inequality that the Euclidean distance of ftu and ftv is bounded from above by L times the Euclidean distance of u and v. Okay, with those conditions, let us assume that we have solutions u and v of the initial value u prime of t is equal ftu of t, with initial condition u of t naught is equal u naught, and v prime of t is equal f of t v of t, with initial condition v at t naught is equal v naught. Under those assumptions, we estimate the difference between u and v at time t. Namely, for every time t after t naught, the Euclidean distance of u of t and v of t is bounded from above by the exponential of L times t minus t naught times the initial distance. So what that theorem tells us is that if we have two solutions for the same ordinary differential equations, but with different initial values at the same time t naught, then the difference between the two solutions for all future times can be bounded from above by the distance in the initial condition times this exponential factor e to the L times t minus t naught. All right, let's get started with the proof. We start with writing down the initial difference u of t minus v of t, and by the fundamental theorem of calculus, that's the difference between u of 0 minus v of 0 plus the integral from t naught up to t of the difference of the derivatives u of s minus v, u prime of s minus v prime s ds. Now, because we know that u and v are solutions to the differential equation, you can also change this as follows, namely this difference is the same as u naught minus v naught plus the integral from t naught up to t of f of s u of s minus f of s v of s ds. Okay, we want to estimate the Euclidean norm of u of t minus v of t. So let's take the Euclidean norm of the difference, and using this identity here and the Triangle Inequality, we see that u of t minus v of t is bounded from above by u naught minus v naught in Euclidean norm plus the integral of t naught up to t of f of s us minus f of s vs ds. Okay, and now at this point, we use this continuity condition. So we estimate this difference of f in terms of this difference between the second variable. So we get that all this is bounded from above by the Euclidean norm of u naught minus v naught plus the integral from t naught up to t of L times u of s minus v of s in Euclidean norm ds. That is only an abbreviation in order to keep the formulas a bit shorter. So what we've shown so far is that d of t is bounded from above by the Euclidean norm of d of t naught plus the integral from t naught up to t of L times the Euclidean norm of ds. So it only remains to estimate the growth of this function d. And what we are going to do is we show this function d of t satisfies this exponential estimate. Now, if you take a look at this inequality, if d of t naught is equal to 0, then the two initial data are the same, and so u and v are also the same. So there would be nothing to show. U and v would be the same. So let's consider the case that d of t naught is actually non-zero, so there's actually a difference in the initial conditions. In that case, we certainly know that the right-hand side of this inequality is non-zero, and what we're now going to do is dividing by this right-hand side. What we get is that for all times t after t naught, we have that 1 is larger or equal to the following fraction, namely the Euclidean norm of d of t divided by the Euclidean norm of d of t naught plus the integral from t naught to t of L times the Euclidean norm of ds. From this inequality, okay, let's multiply both sides by L. So we get L is larger than the same fraction, now the numerator multiplied with L. And now we see that the numerator is actually the derivative of the denominator of this fraction. And we can identify now this expression here as the derivative in time of the natural logarithm of the denominator. So this is the derivative in time of the natural logarithm of the Euclidean norm of dt naught plus the integral from t naught up to t of L times the Euclidean norm of ds. Okay, that derivative is bounded from above by L. And if we now integrate the left-hand side here, L, and this derivative from t naught up to t, we get another inequality, namely L times t minus t naught is greater or equal the natural logarithm of Euclidean norm of dt naught plus the integral from t naught up to t of L times the Euclidean norm of ds minus the natural logarithm of the Euclidean norm of dt naught. In the next step, we apply exponentiation to each of the sides in this inequality, the left-hand side and the right-hand side. So the exponential of L times t minus t naught in absolute value is greater or equal to the following product, namely the Euclidean norm of dt naught plus the integral from t naught up to t of L times the Euclidean norm of ds multiplied with the reciprocal of the Euclidean norm of dt naught. So remember that the Euclidean norm of dt naught is non-zero. So we can actually take the reciprocal of that value. And in particular, we can now multiply both sides of the equation by the distance in the initial conditions, which gives me d of t naught in Euclidean norm times the exponential of L times the absolute value of t minus t naught is greater or equal, well, the Euclidean norm of dt naught plus the integral from t naught up to t of L times the Euclidean norm of ds. And now we are already finished with the proof, namely on the left-hand side here, d of t naught is just the difference in the initial conditions, u naught minus v naught. And on the other hand, we've seen that the right-hand side of this inequality here is already an upper bound for the Euclidean distance of ut and vt for any time t. We just plug in the definition of d on the previous slide. Let's have a look at a very simple example where we can actually estimate the distance precisely. So let's take a look at the initial value problems. U prime of t is equal 3 times u of t, and v prime of t is equal to v times v of t. And the initial condition at time t equals 0, in the first case, u of 0 is equal 26, and v of 0 is equal 35. And as we already know, the respective solutions are u of t equal 26 exponential 3 of t, and v of t is equal 35 times the exponential of 3 of t. So we see that the distance of u of t and v of t is bound from above simply by 9 times the exponential of 3 of t. And that's precisely the distance in the initial condition times the exponential of this factor L times the time that has already passed. Namely, we see that u naught is equal to 26 and v naught is equal to 35. And since the right-hand side of this Cauchy problem can be written as f of t of u equals v times u, we easily find that the constant L can be chosen as 3. So this simple problem demonstrates that this upper bound u of t minus v of t less or equal u naught minus v naught times exponential of L times t, that this upper bound actually is already realized in this very simple example. This tells us that this upper bound that we have derived in this abstract theorem is actually already a very realistic upper bound. Let's take a look at another example that is only slightly more complicated. Namely, we have the two initial value problems. U prime of t is equal the sine of t u times u of t plus t, with initial condition u naught is equal to 11, and v prime of t is equal the sine of t times v of t plus t, with initial condition v at 0 is equal to 7. As we can tell, both these Cauchy initial value problems have the same underlying ordinary differential equation, and in both cases, the right-hand side of the Cauchy problem is the function f of t and u equal sine of t times u plus t. Now, for any choice of time t and state values u and v, we can check the following inequality, namely, the distance of ftu and ftv is bounded from above by, well, the absolute value of the sine of t times the absolute value of u minus v. And okay, the sine of t has absolute value at most 1. So in fact, we get that this all is bounded from above by the absolute value of u minus v. In particular, the constant L in this example can be chosen to be equal to 1. And that gives the following upper bound for the difference of u and v for any time t. Namely, the absolute value of u of t minus v of t is bounded from above by the absolute value of 11 minus 7 times the exponential of t. I've simply plugged in the difference between the initial conditions and the constant L equal 1. In particular, this upper bound can be simplified to 4 times exponential of t. So no matter what the solution is, at least I have this simple upper bound of how small changes in the initial data affect the solution. Now let's also take a look at an example with a vector-valued variable. Namely, again, we have the harmonic oscillator with frequency omega. So the harmonic oscillator is a vector-valued ordinary differential equation. It is linear, and to formulate the harmonic oscillator equation, it is convenient to introduce the following matrix. Namely, M is the matrix with first row 0, 1, and second row minus omega squared 0. Now for this example, let us pick two vectors u0 and v0 from r to the 2, and let's take a look at the following two initial value problems. On the one hand, we have the ordinary differential equation u prime of t is equal m times u of t, where m times u of t is a matrix vector product, and we have u0 is equal u0 as initial condition. And then we have v prime of t is equal m times v of t with initial condition v of 0 is equal v0. And as you take another look at the harmonic oscillator equations, you see that this is actually a very compact formulation for two initial value problems with harmonic oscillator equations in first order formulation, only with maybe two different initial conditions. Now, as you can clearly tell, the function f of tu in this example is simply m times u, this matrix vector product. And the Euclidean distance of ftu and ftv for any time t and any choice of vectors u and v can be written as the Euclidean norm of the matrix M times the difference u minus v. And a very simple calculation shows you that this is bounded from above by the maximum of 1 and omega square multiplied with the Euclidean distance of u and v. So let us take this maximum of 1 and omega square as our constant L. Then we already have all the ingredients that we need for this stability estimate. So we get that the difference of u of t and v of t in Euclidean norm is bounded from above by the Euclidean distance of u0 and v0 times the exponential of L times t. In our very first example, we had seen that the stability estimate is the best possible if we just have very general Cauchy problems in mind. In fact, in our first example, the difference between the two solutions was exactly this upper bound, as in the stability theorem. Now, in the case of the harmonic oscillator, we remember that the solutions are periodic functions, and you remember that the solutions to the harmonic oscillator equations remain bounded. So we naturally expect that this upper bound will be helpful perhaps in the for very small times t, but as t goes larger and larger, this will be a heavy overestimation of the actual error. The frequency for both problems here is the same, so omega is the same. So the frequency of the solutions will be the same, only the amplitude will differ. So to summarize from these examples, the stability theorem is the best possible under these very general assumptions, but in certain cases, it will be an overestimation of the actual difference between the two different solutions with two different initial values. So we have found a theorem that tells us how perturbations in the initial data affect the solution. And now also it says how perturbations in the right-hand side of the Cauchy initial value problem affect the solution. that can be formalized as follows. Let us suppose we have got two functions f and g defined on the real numbers n, both mapping into R to the n, and both are continuous with the following properties. On the one hand, we again have this constant L, which tells us that for all times t and all vectors u and v, the Euclidean distance of FTU and FTV is bounded from above by L times the Euclidean distance of u and v. That's the same as before. And we also assume that then exists another constant m, such that for all times t and all vectors u, the difference between FTU and GTU is bounded from above by m. So we can think of G as a small perturbation of F. Okay, let's take some initial time t0 and some initial vector u0 and take a look at the following Cauchy initial value problems. On the one hand, u prime of t equal f of t and u of t with initial condition u of t0 equal u0, and v prime t equal g of t and vt with initial condition vt0 equal u0. This time the initial conditions are the same, but the right-hand side of the differential equation is different. So under those assumptions, we have that the difference of ut and vt in Euclidean norm is bound from above by m over L times the exponential of L times t minus t0 minus 1 for all times t at least t0. This theorem looks a bit similar to the previous theorem, and in fact, the proof is a variation of the previous proof. For the proof, let's again start with the difference u of t minus v of t, and applying the fundamental theorem of calculus, we see that it's the same as u of 0 minus v of 0 plus the integral from t0 up to t of the derivatives u prime of s minus v prime of s ds. Now this time the initial conditions are the same, so the only thing that remains is the integral, and making the obvious substitutions, we get that this is the integral from t0 up to t of fs us minus gs vs ds. Now again we can apply the Euclidean norm to both sides. So we get that the Euclidean norm of u of t minus v of t, which we want to estimate, is bounded from above by the integral from t0 up to t of the Euclidean norm of f of s u of s minus g of s v of s. In order to get an estimate that we can work with, we apply the triangle inequality. Namely, I subtract inside the Euclidean norm, I subtract f of s v of s, and I add f of s v of s. Then the triangle inequality provides us the integral from t0 up to t of, on the one hand, f of s u of s minus f of s v of s plus the Euclidean norm of f of s v of s minus g of s v of s. In the first Euclidean norm, the f is the same, and the second argument of f is different, u of s and v of s. And in the second Euclidean norm, I've got the difference of f and g with the same second variable, v of s. Now, for the first Euclidean norm, I can just apply the inequality that is satisfied by f. So the first Euclidean norm in the integral is bounded from above by L times the Euclidean distance of u of s and v of s. And the second Euclidean norm can be bounded from above by m, just by assumptions. So the entire integral is bounded from above by the integral from t naught up to t of L times the Euclidean norm of us minus vs plus m. Okay, before we proceed, we again introduce that abbreviation d of s equal u of s minus v of s. Only to simplify the formulas a bit. What we've shown is that the Euclidean norm of d of t is bounded from above by the integral from t naught up to t of L times the Euclidean norm of ds plus m, where s is the integration variable. Now, in order to apply a similar technique as in the proof of the last theorem, I add m over L to both sides. At this point, we can safely assume that m is greater than 0 and that t is different from t naught. I mean, if t would be the same as t naught, we would have nothing to show because u and v agree on t naught by assumption. And m certainly is greater than 0 because otherwise the two Cauchy problems would be completely the same and we had nothing left to show. So in particular, since t is not equal t naught and m is positive, I can already tell that the right-hand side of the inequality is not 0. Okay. Now we proceed similar as in the previous proof and divide the inequality by the right-hand side. So for all times t greater than t naught, we get that 1 is larger than the following fraction, namely the Euclidean norm of d of t plus m over L, divided by the integral from t naught up to t of L times the Euclidean norm of ds plus m, and then the additive constant m over L. Now again, I multiply both sides of this new inequality by L, and I see that L is greater or equal that fraction, which is the time derivative of a natural logarithm. Namely, it's the time derivative of the natural logarithm of the integral from t naught up to t of the function L times the Euclidean norm of ds plus m plus its additive constant m over L. Okay, now I can integrate both sides of this inequality in order to get rid of this time derivative. So integration from t naught up to t gives me now L times the distance t of L times the distance of t and t naught. That is greater or equal to the natural logarithm of the integral from t naught up to t of that function L Euclidean norm ds plus m plus this constant m over L. And the whole thing now minus the natural logarithm of m over L. That's just another application of the fundamental theorem of calculus. Okay, now in order to get rid of the natural logarithm, I apply the exponential function to both sides, and I get that the exponential of L times t minus t naught is greater or equal the integral from t naught up to t of the same integral as before, plus m over L, and the whole thing multiplied by L over m. Again, we remember that m is non-zero. Now I multiply both sides by m over L, and what I get is m over L times the exponential of L times t minus t naught is greater or equal to the integral from t naught up to t of the same integral as before, plus m over L. Now let us recall that the integral here in the very last inequality, we still have that this integral is an upper bound for the Euclidean norm of dt. Now if we subtract m over L from both sides of the inequality, then we already have the theorem that we want. And the proof is complete. Now, in order to get a feel for that result, let's take a look at the following example. Suppose we've got two initial value problems. The first initial value problem is u prime of t equals 3 times u of t, with initial condition u of 0 equal 5. And the second one is v prime of t equal 3 times v of t plus the sine of t, with initial condition v of 0 equal 5 again. So the two initial conditions are the same, but the right-hand sides of these two Cauchy problems differ in one additive term. So putting that into the formalism of our theorem, we have that f of tu is equal to 3u and g of tu is equal to 3u plus sine of t. Okay, well now we verified two inequalities. First, we check that the absolute value of f of tu minus f of tv is bounded from above by 3 times the absolute value of u minus v. So we can pick the constant L equals 3 in the formalism of the theorem. And second, we see that the absolute value of ftu minus gtu is bound from above always by sine of the absolute value of the sine of t, which of course is bound from above by 1. So we can pick m equal 1 in the formalism of the theorem. And so whatever the solutions are, we find that the absolute value of u of t minus v of t is always bounded from above by 1 over 3 times exponential of 3t minus 1. We have analyzed the effect of perturbations in the initial value of a Cauchy problem and the effect of perturbations in the right-hand side of a Cauchy problem. Now, let's combine these two results. Then we have simultaneously perturbations in the initial values and the right-hand side of the Cauchy problem, which arguably is the most realistic situation. For example, in physical modeling. The result can be formulated as follows. Suppose that we have functions f and g from the real numbers times r to the n, mapping into r to the n. Suppose that both of these functions are continuous, and that we have two positive constants L and M, such that on the one hand, for all times t and all vectors u and v in r to the n, we have that the Euclidean distance of ftu and ftv is at most L times the Euclidean distance of u and v. And on the other hand, for all times t and all vectors u, we have that the difference between ftu and gtu in the Euclidean norm is bounded from above by m. Now, if we pick an initial time t naught and initial values u0 and v0 from r to the n, then we can consider solutions to two initial value problems. Namely, on the one hand, suppose that u is a differentiable function such that u prime of t is equal f of t and ut, and u of t naught is equal u naught, and v is a differentiable function such that v prime of t is equal g of t and vt, and v of t naught is equal v naught. Under those assumptions, we have that for all times t greater than t naught, the Euclidean distance of ut and vt is bounded from above by the two terms, namely the Euclidean distance of u0 and v0 times the exponential of L times t minus t naught plus m over L times exponential of L times t minus t naught minus 1. In other words, the perturbations in the initial data and the right-hand side add up to each other. Now we can see that the previous two theorems can be recovered as special cases of this general result. Because on the one hand, if u0 and v0 are the same, if the initial values agree, then the first term vanishes. And on the other hand, if f and g are the same, then m is equal to 0 and the second term vanishes. There are different ways to prove this result. On the one hand, we could just replicate the shape of the previous two proofs, which of course is a bit technical, but certainly possible at this point. But in fact, we can prove this combined theorem by using the previous two results. In fact, we are going to introduce an auxiliary problem. Namely, for the proof, let u and v be two functions as stated as above, and let w be another function defined from t0 up to infinity, mapping into r to the n, which solves the following initial value problem, namely w prime of t is equal f of t wt with initial condition w of t naught is equal v naught. So we take a look at the initial value problem with the right-hand side f and initial value v naught. You can think of it as sort of an intermediate problem between the first and the second initial value problem. From the first problem, we take the right-hand side, and from the second problem, we take the initial value. Let me remark that this problem, this initial value problem, has a solution defined for all times t naught, all times t after t naught, because of this earlier global existence and uniqueness theorem. Now, with this initial value problem, this intermediate initial value problem and its solution w, we see that for all times t after t naught, we have the following inequality, namely the Euclidean distance of ut and vt. Well, it's the same as the Euclidean norm of u of t minus w of t plus w of t minus v of t. Okay, to that term, I apply the triangle inequality. This is bounded from above by the Euclidean distance of ut and wt plus the Euclidean distance of wt and vt. If I take a look at the first Euclidean norm of this first difference, u of t minus w of t, then I see that the associated initial value problems only differ in the initial values. So I've got u at 0 is equal u naught and w of 0 is equal v naught, but the right-hand sides are the same. So I can bound this term by the upper bound that we derived in our first stability result. And for the second Euclidean norm, the difference of Wt and Vt, I apply the second stability result, which gives me an estimate of what happens if the initial values are the same, but the right-hand sides of the Cauchy problem differ. And gives me the second upper bound. And what we see now is that we precisely have the term that we wanted. And the proof is complete. This technique of introducing intermediate auxiliary problems is quite important for proving results in numerical analysis. And if you ever do graduate level research in numerical analysis, it's a technique you will frequently use. So let me try to make this a bit more memorable. Suppose you want to estimate the distance between two mathematical objects that differ in maybe more than two ways. What you do then is you introduce an auxiliary object which differs from the other two objects in only one way each. The technique that we frequently use is adding a zero. If you want to estimate the distance between two objects, you introduce an auxiliary object, subtract it from the first object and add it to the other object. And in that manner, you can reduce the original problem of comparing two mathematical objects that differ in maybe more or two ways to the probably simpler sub-problem of comparing mathematical objects that differ in only one single way. We've used this type of technique in the previous result, and I think you will quite often encounter it throughout numerical analysis. Okay, on that happy note, let's do another example. So let's suppose I've got two initial value problems. U prime of t is equal 3 times u of t with initial value u of 0 equal 5. And let's say v prime of t is equal 3 times vt plus sine of t with initial value v0 equals 7. We can apply now this previous result, which estimates the effect of perturbations in the right-hand side and the initial values. So putting this into the framework of the previous result, we had f of tu is equal 3u and g of tu is equal 3u plus sine of t. Now we see that f of tu minus f of tv in absolute value is bounded from above by 3 times the absolute value of u minus v. So again, we have L equals 3. And the distance of ftu and gtu can for all times t be bounded from above by 1. And okay, applying this previous result, what we get is that for all times t, the distance of u of t and v of t is bounded from above by 2 times exponential of 3t plus 1 over 3 times exponential of 3t minus 1. I would like to finish this presentation with a more general result that covers the case when the right-hand side of the initial value problem is not defined for all times t and all states u. We might not necessarily need this result, but I would like to have it covered for technical reference. So let us suppose that we have a set A, which is a subset of the real numbers times r to the n. And suppose we have functions f and g, which are defined on A and map into r to the n. And let's suppose f and g are continuous. Let us also suppose that we have times t0 and t1, where t0 is smaller than t1. And let us suppose that we've got vectors u0 and v0 in r to the n. And let us suppose that we've got differentiable functions u and v, which are defined on the interval from t0 up to t1. These functions map into r to the n. And they have the following properties. Namely, for all times t from t0 up to t1, I have that t ut and t vt, the pair containing t and ut, and the pair containing t and vt is always contained in A. I've got that u of t naught is equal u naught, and v of t naught is equal v naught. And I have that u prime of t is equal f of t ut, and v prime of t is equal g of t vt for all times t between t naught and t1. Now, if there exist constants L and M which satisfy the following inequalities, namely for all pairs tu and tv in the set A, we have that the distance of ftu and ftv is bounded from above by L times the distance of u and v. And for all pairs tu from the set A, I also have that ftu minus gtu has Euclidean norm bounded by m. If those assumptions are met, then I get the inequality as in the previous result, namely for all times t between t naught and t1, I have that the Euclidean distance of u of t and v of t is bounded from above by the Euclidean distance of u naught and v naught times the exponential of L times t minus t naught plus m over L times exponential of L times t minus t naught minus 1.